so we are now in the next chapter, process synchronization. Don't really remember the chapter number right now, guys, but I'm kind of excited because as I was just talking to our media crew here, Nick, who you can't see, we have actually just finished the last chapter. So it's the first chapter complete right now. Yeah, I don't know if you guys are excited, but I'm excited that there's actually like a whole set of videos done, okay? It's like progress. Anyways, now what we're going to be talking about is process synchronization, right? So we've talked about basically this ways, right? You can break up programs, right? Make them run in parallel, right? We have different processes, different threads. Well, the problem is we can only really do simple things if we have threads at all. Basically are independent, right? Really, what would be nice, right, is we have threads that can basically talk to one another, right? I can do some computation, send that information to somebody else can act on it, and they can maybe send it back, right? That is very useful, right? And I'm not saying that these threads have to talk to one another all the time because then that'll slow down our overall process. But overall, I want a way, right, to communicate between them, right? So that's what we're going to take a look at. And the reason this whole chapter is called process synchronization is because there's a moment, right, of when things are in sync. I'm not sure what word I'm looking for, but right, I need these things to line up, right? If a thread wants to communicate with another thread, they have to at some point, right, in the runtimes match up, right, be synchronized for just a moment so that messages can pass, right, data can flow. Or sometimes, right, they'll be doing things that maybe impact the other somehow, right, and they need to make sure they wait for the other one to do something first, right? Maybe it's not directly a message being sent, but it's just kind of I got to wait for you to finish what you're doing. So that's what we're going to be talking about. Now, the first bit we're going to be talking about here is just kind of some general background and really showing why it can be hard sometimes to make different threads work together, right? It's going to be unfortunately a little bit difficult, right? Even on top of the problems you already have, taking a program, breaking it down, and making these little independent pieces out of it, even above that, we still have problems. We have problems in the execution engine of this stuff, right? How do we actually make this stuff run on the CPU? That's where we're going to get into trouble on a few things. All right, so moving forward, what do we got? All right, so if we have threads or processes running independently, fine. There's no problem there, right? We're not going to have anything, running over something else, right? They don't need to collaborate anyway. That's fine, but that's boring, and we can do better, right? We can do better. So what we're going to start with is actually kind of defining a classical problem of concurrency, which is called the producer-consumer problem. Basically, what we're saying is we have two threads or two processes. Sometimes I'll be a little bit lazy here, right? Really, I should be saying threads all the time, but usually I just say process, right? Point is I have two things running at the same time. I have two of these things running, and one of them, right, is the producer, and one of them is consumer, and there's some shared pool of things, right? I have a collection of items, and so the producer's job is the producer does some magic, right? Producer creates an item, and that item needs to go into that collection, right? Say that there's an array out there. Then that consumer, right, the consumer's job is to wait for that array to be non-empty, and once it has something in there, take out an item and consume it, right? So I have two processors running at the same time, working side by side, right? One whose job is to build stuff, one whose job is to consume stuff, right? So this is a classical problem, right? We'll actually try to address it, right, in a few different ways, right, in a few different libraries. We'll use it a bunch of times, right? Actually, if you want, you can maybe think to yourself, where is this problem coming from? And you should actually be able to, maybe come up with some ideas of what are real-world problems that look like this thing called the producer-consumer problem. Maybe one example, right, is like web servers, right? Your clients, right, or maybe are a bunch of producers, right, that are producing requests for web pages that maybe get consumed by your server, right, has to maybe update a database, right, or maybe generate a page or something like that, right? But you have basically two things working in parallel, right, and there's kind of data passing between them, right? So server would be one example. I would suggest you think to yourself, maybe you can come up with some other examples as well. There are a lot of them. Okay, so let's go ahead and walk through the code a little bit. So the code itself, right, up at the top I have kind of it listed there as what is shared data, right? So we have counter, buffer, in and out. Basically, our counter variable, right, that's going to count the number of items I have out there, right? Things that the producer has built that haven't been consumed yet. The second thing I have, right, is buffer, and what buffer is going to be is that shared array, right? So we're introducing kind of the idea of shared memory that everybody can make changes to. For now, we can kind of just pretend like, they're not going to interfere with one another, right? They're not going to overwrite one another. Well, that's going to be a separate problem. We can just leave that buffer, alone for now. Then we have the last two things in there, which are in and out. Those are two indices into the array. So what in is representing is what is going to be the next space that I can put a new value into, right? So where is the next thing produced going to go, right? It'll go in the index that in is pointing out. Then I also have the index out. Out is basically going to be the index of where do I put the next thing that I build, right? So you can maybe picture, right, as you have, an array, right, and your array, looks something like this. Bunch of slots, and then you just have, right, somewhere along there, right, is kind of your, your out pointer or your out index. Over here is, your in index, right? These two variables, right, kind of keep track of, I have stuff over here, stuff over here, stuff over here, stuff over here, right? So they're kind of providing the bounds, right, within the array. The stuff exists, right? One thread is going to be adding to one side, one thread is going to be removing from one side. Now, kind of one note here is that what's going to happen is that these things kind of wrap around, right? So later on, you'll see a modulus in the code, but basically the idea is, if I'm putting new things in there, right? If I'm continuing, to fill up this array with a bunch of things, what will happen is it'll roll around, right? So maybe I fill up this slot, maybe I fill up this slot. What will happen, right, is once I fill up that slot, I'll basically wrap around and I'll start filling up from the other side, right? So these are working a little bit like a circular queue. You guys may or may not have seen circular queues before. Usually they're taught in either SER334 or SER322. But then, some of you have had me for 222. In 222, I stopped teaching circular arrays because I thought that the SER300 teachers did them, and they did. But then I started teaching 200, and I stopped teaching circular queues in that because I thought the 222 instructors would do it. And so it turns out that if you've taken me for both classes, you probably haven't seen that stuff. So, sorry. Anyways, you kind of seeing it here, right? The idea is, right, is I can have this data structure that wraps around, right? I don't have to kind of wait. I don't have to stop once I'm at the max value of the array. What I can do is I can basically add one and do a modulus, and that'll naturally wrap me around to be at the first position in that array, right? So then I can kind of restart and I can go on, right? So picture you have a circle. So that's what we're going to be doing here. Now, if we look at the code, the first thing I have is the code for the producer. The producer's code is basically going to say, okay, I have this infinite loop, right? I'm infinitely trying to produce things, right? The other one is I'm infinitely trying to consume things, right? They're going to run forever. That's fine, right? It's just part of kind of our conceptualization of this problem. But then what I do, right, is I have to wait around first for, basically, I need a free space, right? So I have here this code that says, counter equal buffer size, just loop, right? I notice that this is basically busy waiting, right? See over here, there's a semicolon at the end. There's no actual code within that while loop, right? There's no body, right? It's just going to sit there until that condition ends up being false, and then I'll exit out, right? So that's actually in a 4-sec program there to wait until it has a space to add something. So say that happens, right? All of a sudden it frees up, there's space. While we go to the buffer at the index indicated by n, and we put the next item in there, right? That next underscore produced is the thing that this producer thread, our producer process has just built. Put it in there. Okay, and then we do in, and we do basically in plus plus, but notice there's the modulus there, right? Because we want it to wrap around, right? If we get to the end, we want to just start again at the beginning, right? Because of that while loop check at the beginning, we are guaranteed that there will be space for the new thing we're producing, right? So we don't have to worry that we wrap around and then we override something. No. It's going to be okay, right? Because we have that initial check to ensure that there is space, we will be okay. And at the end, we have counter plus plus, right? So counter increases by 1. I'm looking at the camera a little bit weird because this is going to be the line that gives us trouble. The rest of the lines are pretty good, but this counter plus plus, a little bit of trouble later on. So that's this code here. Jumping down to the consumer, right? So we did the producer above. Call this P, this is C. In the consumer, right, code is most of it's symmetric, right? So first thing we have is our while loop. So we loop, right, while there's nothing to consume, right? In this case, we check while counter is equal to 0, right? Well, if it isn't, we just loop there, right? You can see again the semicolon at the end is just hanging out there. There's no code being run. Once it exits out, right, once it's false, right, then we can drop out and we can run our code. So then what we do is we say, okay, I'm going to go and grab out the next thing from the buffer, right, which is our thing located at out, right? Take that, put that into next consume, right? Next consume is going to be something we deal with, right? Here there's just a comment to say, we consume it, right? But something has to happen to that value we took out. Once we do that, right? Once we take out the value, we can move up our out variable, right? So basically, we're moving forward and saying, okay, I'm done with that. That space is now no longer used. The next thing that I should consume, right, will be the next thing that's to the right-hand side of it. Basically, right, it's equivalent of doing that plus plus on the variable. Then my last line is counter minus minus. Well, makes sense, right? Counter is supposed to be the total number of things I have in that buffer. I've just consumed one, so I'm doing minus minus. So that should be good, but again, it's going to be one of the lines that gives us trouble. Well, it's going to be the line that gives us trouble. Okay. So maybe think about that for a moment, right? This producer-consumer problem, and look at the code. Now, our problem is going to be this. I have these two programs running. Instead of just having to worry about, oh, what is the program doing on any particular line, I need to worry about how these programs interact at any particular line, right? So if this has maybe 10 lines in there, normally you think to yourself, oh, I have 10 different states the program could be in. Well, if I have two programs of length 10, well then it's 10 times 10, right? For any position in the first program, the other program could be on a different position, right? So I have from 10 different states to consider, 100 different states to consider, right? Any combination of those two programs now could occur because I'm allowing them to interact independently. And this is where I get into trouble, because there's going to be some things that if I let them happen at the same time, or let them happen in the wrong order, stuff will break and life will be very, very bad for us. So that is our issue. Now, glancing at this code, you might think, oh, it's fine. Can't really tell any way that would be a problem. Well, that's because C is still a high-level language and it's hiding some stuff from it. So let's break down the code a little bit to see how it'll be executed, and then we'll have an idea of where our issue will occur. So over here, I have the same programs here. And what I've done is I've broken down the kind of the last line there that changes the count variable. So over here, right, this used to be a count plus plus. This over here used to be a count minus minus. What I've done here, right, is basically I've written it as from being that one line, right, the one increment or the one decrement, to being kind of three operations that it would end up being, in terms of assembly, right, the three lower level things, right. So first thing we have in there, just looking at the left hand side, saying, okay, count plus plus, what does that get compiled to? Well, the first thing it gets compiled to is, basically I have to get counter from system memory, put it in a register, right? So I'm loading a register. That's one step, right? Once it's in a register, then I can increment it, right? Once it's incremented, then I can take that value and store it back to system memory, right? So even though to us we maybe are used to seeing that increment as being just one operation C, really it's three, right? In terms of the assembly operations that'll be generated when you actually compile the thing. So this is our first note, right? And this is where you can see we're adding some complexity here, right? And there's going to be a chance where things can go wrong when you're running these things in parallel. On the right-hand side, same pattern, right? Get stuff from main memory, store in the register, decrement it. Store it from the register, back to main memory. Okay, so this is our producer, this is our consumer. Now what we want to try and do is kind of imagine how these things might interact. And the term I'm using for this, which isn't actually the correct term, but the term I'm using is program slice. So program slice, basically I'm saying is, okay, picture, right, is that you're at line 5 here, and then line 7 over here, right? So you picture you're sliced into your program, right? You have some lines here, some lines over here, right? Could be kind of any snapshot you take of these things running side by side. You would be kind of highlighting what are the current lines they're on, right? That's what I'm referring to as a program slice. So we can imagine kind of slicing across this thing. So let's say our program slice, just for a moment in time, let's say, is going to be, let's try this. This should work out. I'm trying to get under the register read on one side, over the register read on the other side. So imagine we have that for a moment. That's kind of where we take our snapshot. Now let's say, right, that the producer is trying to produce something, the consumer is trying to consume something. And let's say the counter initially is equal to 5. Okay, in the producer, 5 comes out of the counter, gets put on the register. Okay, fine. So that's kind of one step. And then maybe, I don't know, let's say that the next line in producer runs, register gets incremented by 1, right? So the register right over here is going to have, say it's going to have, initially a register, we load the 5 into it. We do the increment, now the register has 6 in it. Okay, doesn't seem to have gone on yet, but remember the other thread can do whatever it wants, so it can continue running. So let's say the other thread continues running, right? And it does, this register over here, register equal counter. Well, in this case, right, when we load from memory to register, it's going to grab that 5, right? That 5 in system memory is still just a 5, right? That 6 only exists in the register that the other thread has, right? It doesn't exist in main memory. So when my consumer is going and is trying to read that counter value into a register, it gets the old thing, the 5. So over here, right, this is going to be equal to 5. And now you can probably see there's going to be an issue, right? Maybe it proceeds again, right? It does another line over here. It does register minus. So over here, we have the number 4, right? I'm trying to do slashes here to show these are like a comment. I know they're not too vertical, but just assume it's a comment. Now we have the number 4 there, right? So the producer in one register, right, has the number 6, the consumer in the register has the number 4. Now, both of those are going to go and write their value back into main system memory. Problem being, who gets there first, right? So if the producer runs first, it'll write a 6. Fine. But then the consumer runs. Well, the consumer will go and write a 4, but that 4 replaces the 6, right? Or if they go in the other order, right? Maybe the consumer goes first, it writes the 4, and then later, right, that gets pushed out, and we write a 6 on top of it, right? So those two things are basically competing with one another, right? We want to have, well, at the end of the day, right, there's going to be some value in system memory. We would expect, right, that it would be 5, right? You add, and you've consumed one, you produce one. Should be where you started at. Problem is, based on this order, we'll either get that 4 or we'll get that 6, right? One of them will kind of be the person who has final say, right? And that is our fundamental problem, right? These things are competing, or what they're saying, what the terminology typically is that they're racing, right? So this is actually what is called a race condition. So a race condition means that we have two programs that are running side by side, and based on basically what runs first, we'll get different outputs. This is very bad because we don't have any control over what gets run first, right? Sometimes it'll be this thread that will go get there first. Sometimes this thread will get there first. That's bad because it gives our program kind of inconsistent output. And I mean, it's a computer program, so we should always get the same result from it. Now, this last slide here basically just has the terminology again. So again, the idea, right, is this is a race condition, right? So who gets there first, right, will change the output of the program, right? So if producer gets there first, right, we get that 6, consumer gets there first, or, well, producer gets there first, it's going to end up being a 4. Consumer gets there first, it's going to end up being a 6, right? Whenever we have that issue, right, of the order of execution, changing the output, we say that's going to be a race condition. And so what we're going to do in the following sections is try to find out mechanisms to prevent that from happening, right? We want to make sure that no matter what order these things are executed in, right, because we don't really have control over that, we'll always get the same result. And what we'll end up doing is basically saying, okay, I'm going to say that only one person at a time can mess with the counter, right? I'll make that kind of an atomic region. Right? So that'll be a solution that we take a look at in the next section.